Consider the combustion of urea. Suppose 3 grams of urea were burned in excess oxygen in a fixed volume 1 liter sealed container that initially contained 2 atmospheres of oxygen gas at 298 Kelvin. Estimate the final pressure in the container at 298 Kelvin. To get the final pressure, we use the ideal gas equation, PV equals nRT. Which we need to rearrange in order to solve for P. In this equation, N is the number of moles of gas. Based on the information given in the problem, the gases we expect to find after the reaction occurs are carbon dioxide and nitrogen, as well as the leftover oxygen. By now, you should be able to calculate moles of reactants and products involved in a reaction. Here's how it's done in this case, step by step. First, we calculate the initial moles of urea and oxygen. The molar mass of urea is 60.06 grams per mole. Therefore, 3 grams of urea to moles of urea corresponds to 0.04995 moles. Using the ideal gas equation, we can calculate the initial moles of oxygen in the container. The number of moles of oxygen is equal to the pressure, 2 atmospheres, times the volume, 1 liter, divided by the product of the ideal gas constant, R, and the temperature in Kelvin. R is 0.08206 liter atmosphere per mole per Kelvin, and the temperature is 298 Kelvin. Carrying out the indicated calculation, we find that we initially have 0.08178 moles of oxygen. Since we are told that there is an excess of oxygen, we assume that urea is the limiting reactant. Complete consumption of 0.04995 moles of urea will yield 0.09990 moles of nitrogen and 0.04995 moles of carbon dioxide. Here's how we calculate the amount of nitrogen produced. We start with moles of urea, then multiply it by the mole-to-mole ratio of nitrogen to urea. The balanced equation tells us that 2 moles of nitrogen are produced for every 2 moles of urea consumed. This calculation gives us 0.04995 moles of nitrogen. Similarly, complete consumption of 0.04995 moles of urea will yield 0.04995 moles of carbon dioxide. To get this, we multiply moles of urea by the mole-to-mole ratio of CO2 to urea. The balanced equation tells us that 2 moles of CO2 are produced for every 2 moles of urea consumed. To calculate amount of oxygen consumed, we multiply the amount of urea consumed by the mole-to-mole ratio of oxygen to urea. According to the balanced equation, 3 moles of oxygen are consumed for every 2 moles of urea. This gives us 0.07492 moles of oxygen. Subtracting the amount of oxygen consumed, 0.07492 moles, from the initial amount of oxygen, 0.08178 moles, gives us the amount of unreacted oxygen gas, 0.00686 moles. Adding up the moles of carbon dioxide, nitrogen, and unreacted oxygen gives us a total of 0.1068 moles. Now that we've figured out the total number of moles of gas molecules to be 0.1068 moles, we have all the values we need to calculate the final pressure of the gas. The final pressure is equal to the total number of moles, 0.1068 moles, times R, 0.08206 liter atmosphere per mole per Kelvin, times the temperature, 298 Kelvin, divided by the volume, 1 liter. Carrying out the indicated calculations gives us an answer of 2.61 atmosphere. Note that we are only keeping 3 significant digits in the final answer. The pressure increases from 2 atmosphere initially to 2.61 atmosphere. This is typical for combustion of nitrogen-containing compounds. The production of gas generally leads to increased pressure if the combustion were confined, and this is the reason nitrogen-containing compounds are used for explosives. This answer is an estimate because significant deviations from ideal behavior do occur at high pressure, even at 1 atmosphere. We are looking at an error of about 1% in values based on the ideal gas equation. We also assume that the volume of urea and water are negligible. This is generally a good assumption to make. This reaction produces about 0.01 moles of water, or 0.18 grams of water, which will have a volume of about 0.18 milliliters, much smaller than the total volume of 1 liter. We are neglecting the vapor pressure of water, which is about 23.8 torr at 298 Kelvin. Finally, we are assuming that there are no side reactions. Since we have an excess of oxygen, it is in fact possible for the nitrogen product to be further oxidized. A much larger excess of oxygen will also be needed to eliminate the possibility of incomplete combustion, which produces carbon monoxide instead of carbon dioxide.